This talk is going to be about a little bit details of trace filtering and specifically what's going on inside LTTng. In the end, I'm also going to describe a little bit about eBPF. Before I start, some people had questions. I would clarify that uh, like in an official release, it's not there. It's all experimental for now. The support of eBPF with LTTng. So there were some questions like that. So I'd just say that it's more like an experiment that I've been doing and like exploring it further. I am Suchakra. I'm a PhD student under Professor Michel and the Polytechnique Montreal dorsal lab. So I work on debugging, tracing, and JIT and all that stuff. So this talk we are gonna have like three major points of discussion, and the first is I'm gonna tell you about LTTng's trace filter. We'll learn what filtering is like even before that. I'm sure everybody knows that, so I'm just gonna like run through it. And then LTTng's trace filters, how they have been designed and how they are different from other filtering which we see. And then I'm going to talk about eBPF, its mechanism, what's going on with eBPF right now, what's the current status of eBPF, and a little trial which I did with eBPF and LTTng, how I used it for filtering both at the kernel level and at the user space level, and small experiment to see how it performs and how the LTTng's filter interpreter performs and how the eBPF filters perform. But I should tell you that eBPF is now more than just normal filtering, so it's like evolved. And then I'm going to discuss about something beyond. This is something which is not yet clear, but you know, I mean, we are all here, so we can probably have a good discussion about it. So, filters. This is a filter. No, it's a funnel, but it's a filter. So, what do filters do? You have some input, and then you can probably get some output which is restricted based on a filter. So in a traditional context, you can have a small filter like that, and to which you submit some packets, and these things, each of these things are called predicates. They can be true or they can be false, and then you can get a very restricted data out of the huge number of packets which you are giving. So what about evaluating these filters? You have these expressions, you have everything, but how do you evaluate the filters? So you have some packets which you give to the filter. So what you can do is, let's consider a small evaluator like a foo evaluator, which takes the whole filter string and then you can like parse it by hand each and every time, and then you can find out whether it's true or false to say keep the packet or drop the packet. I'm talking about packets because it was like a primary use case. So imagine you run it lots of times. You're going to lose lots of time there, you know, just by evaluating it. So you don't. So the foo evaluator is a part of which you don't want. Okay, it's an overhead for you. You want to minimize that. So we have another structure. We have like a bar evaluator, which now has two parts. One is a bar generator, which takes in the big expression as a string, and then you can parse it and generate a syntax tree out of it, then generate a intermediate representation, and then save it as bytecode. Now then you can send this bytecode to its own small interpreter. These small VMs we call as process VMs, and then you have like a true or false when the filter runs. So when the filter actually runs, it just keeps on going through the bytecode, and you don't have to do all that step before. It's just like a one-time step which you do. So you save a lot of time, okay. But what you can do beyond this is that you have a JIT compiler. So instead of having a bytecode before, we take the bytecode and convert it into the native code. And this native code is the code which will directly run on your machine. So what you can do now is just run over the native code. It exactly looks like a very small function and it runs in native. So you save a lot of time there. And over in time and in all the research that has been done for a long time, this is not new, this is very old. And things which we are seeing, we find that native code and jitting it and running in native code saves a lot of time. So, but why do we need fast filters? Okay, why do we need all these blazingly fast filters which are there? So, the primary use case, which is network, we want to sustain network throughput. Okay, we don't want packets to be lost somehow just because you were delaying it because of filtering. Okay, so to sustain this huge network throughput, we really need fast filters. And as the devices are progressing, and everybody knows that even the filters are now directly in hardware. So as devices are progressing, we really need hard filters, which perform very well. So the second use case which I'm more interested in is tracing. So tracing is not now very constricted. It has really evolved a lot over these days. We have big systems just like distributed systems, which we were just discussing before, and those can give you a big flood of events. So we want to filter out all of them. Another thing is that you would say that probably we can just save it and do all the analysis later. Yes, that's possible, and that is indeed being done. But on systems which are like very restrictive in their resources, you would like to at least do some preliminary level of filtering before. So the good use case is high frequency and long running events. That's what I always say. So, but then how do you evaluate an expression like that each and every time? So let's look at, we'll look at two filtering approaches. One is with LTTng and another with eBPF. Though they are not same right now, but at some point of the time they were. So let's start with LTTng's trace filtering. So those of you who are not aware of LTTng, it's just a small part of the LTTng which I'm showing and which is more relevant. So this is LTTng UST, the user space tracer. So you have an instrumented application, and you have, whenever a new event is, whenever you set a new event, you can like manage it with two basic parts of LTTng, the session daemon and the consumer daemon. So whenever an event is registered, the session daemon takes care of it, and it sets up an event consumption. And shared memory is created, and there's a ring buffer between the application directly, and every time the data is generated, you can directly consume it and generate a trace or do much more with it than just in generate a trace. So we are interested in this part of LTTng. So you have your application and you have a new event, but what happens when you set a new filter over it? Or what happens before the event is like sent to the session D for management further? Okay, so what happens is that first whenever you create the new event, you check for a filter whether the user has set up a filter or not. Okay, so you check whether there's a filter. Yes, user sets a filter. So you parse it, you generate the syntax tree, and then you generate the IR, then you generate the bytecode, and then you send it to session D. After the IR generation, there is a small validation. Yeah.
Just a few words. This is not the instrumented user space application that does all this. This is a client. So the LTTng command line client.
Yeah, this is the client which is doing. I mean, all the steps like check the filter, parse IST. This is what the client is doing, and not the application.
Yeah.
Okay. Application is not doing anything right now. It's gonna do soon. So this is what happens, and the filter is now ready with the session daemon. And then what happens is that you send the bytecode to the instrumented user space application, and this is where the next part of the filtering kicks in, where you validate the bytecode which is there, and then you link the bytecode to the event which has been enabled, and then you interpret it. So now every time you keep on running that, every time you hit that event, this small interpretation part will keep on running, and you can then get your filtered events. So yeah, just to like reiterate what Matthew has said, that this part is being done on the LTTng client side. When the and this is part of actually. So this user space application only does nothing right now, but it kicks in when you send the bytecode and it finds that the event is enabled. So this is how you create a filtered session. You create a small session and then you enable the event, and it says that the event has been created. Then you start, then you stop. This is like a normal flow of LTTng, but this is a filtered flow. So what we just discussed before is what is happening when you do LTTng event filter, like the starting part of it. So now we'll dig deep into it, how each of those steps which we just saw before happen. So the first part is generating the bytecode. Generate filter is the function which you find in the client side, which generates the bytecode, for you. But what happens in each of these is that LTTng has a very custom written, handwritten Flex Bison Lexer parser, Flex Bison based Lexer parser. So there's custom grammar for it, and there are a bit of restrictions, and we'll see that. So the first is we do filter parser context allocation, and you run it on the fmem, which is like the filter string you have. So it allocates and initializes the parser, the syntax tree, etc. And then filter parser appends AST and set visitor set parent. What it does is that this is the main part in your Lexer parser, like the YY and YYLex, these functions which run, and they generate a syntax tree for you. So when these functions run, you'll find like a syntax tree like that, where you'll have, for example, we were talking about a filter like foo equal to 42 ampersand bar equal to baz. So you have a syntax tree, something like that, like a representation of a syntax tree, and they are classified when the visitor set parents goes according to ID, a constant or a string. So a certain kind of small specialization is being done. You can call it specialization probably. So you set what kind of a node it is. Is it an operand? Is it an operation? Is it an ID, or is it a constant? Next next what runs is filter visitor IR generates. So it's a handwritten intermediate represent generator which goes through each and every nodes and recursively, and then classifies that what kind of operation it is. So it generates it generates a little bit of IR for it, but at the same time, the main thing is that there is a small check which is done to just see that none of the operations are binary arithmetic or not. If they are, then it just says, oh, they are not supported. So only logical comparisons are supported for now. So then the next is filter visitor IR, check binary operator nesting. So these are some basic checks which are being run. So you accept logical operations, operator nesting, etc. is not allowed. We only allow nesting of logical operations. Then you validate the literal string as literal paths. So you see that no wildcards are allowed in between. For example, if you have like a star, the star should be always in the end if you have a wildcard, so it cannot be in the middle. So all or unsupported characters. So this small validation is done. Then the final bytecode is generated, where we traverse the whole tree post order, and based on each node you start emitting the instructions, and you start saving those instructions in the bytecode. So this all saving is done in the context structure, and then the context structure is made with the bytecode field, and then you send it to the LTTng session B. So now what happens when the event is like okay, ready, and it finds out that the filter is there? How do you start interpreting the filter, interpreting the bytecode? So the main function here is LTTng filter event link bytecode. So as I told you before, the event the bytecode has to be linked to the event, and a runtime has to be generated. So we copy the original bytecode to the bytecode runtime, and we apply some context relocations. And LTTng filter validate bytecode is used for that starting. So this is like the second step of validation which happens before. So there is the first small validation which is done when the IR was generated, and this is the second validation which is done just to check if the bytecode generated is okay. So we see if there are no unsupported bytecode. We see the range overflows for different instructions classes. So if it's like a integer, so you want to see that the context, etc. It's not a range overflow for that. Then you validate the current context and merge points for all instructions. So this is a bit detailed, and I can like probably talk later about it. So then we have LTTng filter specialized bytecode. So this is a small specialization we done because we now know the event field type, so we can specialize the bytecode a little bit further. So this is like very much handwritten. Okay, it looks like a very small compiler, if you may. So the final function which interprets the bytecode is the LTTng filter interpret bytecode, which we were seeing. So the LTTng machine is actually quite interesting. It is a hybrid virtual machine. So it's a stack-based machine. So the two registers like AX and BX, they are aliased to the top of the stack. So every time, so it gives you the flexibility of running in a stack machine, but also it gives you a bit of speed, because always the top and top minus one are AX and BX, and you can directly access them. So this is, for example, a small. I forgot to tell you about the interpreter. The interpreter is threaded instruction dispatch, or it can be a normal dispatch if threaded instruction dispatch is not supported. That is, the compiler is not supporting labels as addresses. Yeah. So this is one small example of that dispatch. Let's come to an interesting part, eBPF. So eBPF, which started with the Berkeley Packet Filter, has had a very similar approach. You have filter expressions, you take the bytecode and then you interpret them. It was very fast, and it is register based and had a switch dispatch interpreter. So it was a very good machine. Like, I'm talking about the BPF, which was just before, but now the BPF has recently evolved, and by the efforts of people at PlumGrid, LXC, etc. And they have done extensions for trace filtering. Yes, kprobes are supported. You can directly create your scripts and then hook onto the kprobes with eBPF. So it's more than just filtering. It could have just been a very small filter. You give some script, you give some filtering expression, it will filter. But now it has evolved a little bit more. I would say more than just little, but like huge. And also the filters are jittered, so they are very fast. Okay, so we talked about LTTng's interpreter. The bytecode was still being interpreted and not jittered, but here the bytecode is jittered and it's really fast. So the main aspects of the extended BPF is that it has some data structures called as BPF maps, like abstract data structures, which can be used for sharing data between the kernel and user. And you have BPF syscall, which can be used for aggregation of data from the kernel and then sending it to the user space. And you can use it to access those shared maps. You can use it to load your program, BPF program, which you just created. There are more registers, 64-bit registers, 10 now, and instead of the 2 registers which were there before. And there are backjumps. Backjumps are also allowed now, and tail calls are also allowed. And there is a very nice verifier for the bytecode, which is very elaborate. We can probably have a complete session on the verifier itself. So how does BPF in the new world work? So you have a BPF filter expressed as in a restricted C format. We are going to see how it looks. And then you have an LVM based backend which can convert it into a BPF based object. So it's like a BPF executable, but it cannot be executed just right away. It's just a collection of different sections and data in those sections. So to use this kernel part of the BPF, we need a user part. So in the user part, what we do is we just load this complete BPF based object, and we can go through each of the sections and the section headers, and then we can take out the bytecode from that. And then through that syscall, we can send this to the kernel part of the BPF, which is the BPF machine which is present in the kernel. So through BPF syscalls, we can do that. Now BPF, so I told you that their BPF now supports kprobes, so we can have BPF tell that, okay, now this small program, the small kernel program bytecode which I have, the BPF bytecode which I have, has to be run at each hit of this kprobe. So we have, so for example, we have a kprobe at BLK start request, and whenever this probe is going to be hit, this program is going to be executed, and we aggregate some data from that and save it into the BPF maps, which I just told you is some data structure which can be used. And then we can make another syscall from the user space program and access these maps. We can read these maps and make we can show them and generate histograms and do all the cool stuff with it. So this is one example session of how eBPF works these days. So this is a filter which I wrote I mean few months back. It's a simple filter which would and this is merged with LTTng. So I wrote it as a part of a module, as a part of LTTng, module. So you could like so it would do what I'm just writing above, like dev name equal to LO, then the dev name is taken from the netif receive skb event. So it's gonna put a trace point there. So, and the bytecode, I actually wrote it like that. Nobody writes it like that, and it was just I wanted to check at each and every part what is happening in the bytecode. And if you are very much interested, this bytecode gets converted into gets converted into native code, and it's a one-to-one just direct method JIT. You can see it's really structured as if it's a function. You have all the function. I mean the first part of the function and the end part of the function, and where you make some space on the stack and you save the callee registers, you clear the registers, then you save the values, and here you do some check over what your context was right now, and then you can restore. So it's you know, I'm not sure if you're really interested in all that. So the next part is about a little bit this thing a little bit more usable, okay, because in this format you have to create another C file and then you have to create another user space program, so it looks a bit less usable. So what happened is that a new thing called as BCC has been created, BPF compiler correction. This project is also being done by the PlumGrid guys. So yes, but it's not directly like a command. So you can go to github.io/bcc to see what it does. So what they have done is, now you see the kernel part, the foo_kern, which is like a restricted C format for BPF scripts. It can directly be used by a Python-based file. Okay. So and then the user space Python part is easily going to access and easily going to share whatever was being done by the same user space C part. Okay, and this is like the BPF filter for which is like the kernel part of the BPF, and this is the user space part. So here you can see, for example, we have to define the BPF map, which we call. So we just do a BPF table which defines a hash table, and then we just name it. We tell it that what kind of the structure this hash table is going to have. Then this is a BPF function called as count sched. Okay, so what we see here is in the user space program is that we can just directly do b equal to BPF, and then we give it the kernel part of the BPF, and then we can load the function count sched, which is the user space part, which is the kernel part, and the actual BPF function which is going to be executed every time the kprobe is going to be hit, and then we attach it to kprobe. Okay, BPF attach kprobe, and we attach it to this kprobe. Okay, and then we can like fetch data from it. For example, we already defined here stats equal to b.get table, so it gets these stats, and then we can like do some pretty printing with it and access it. So it's a very easy way. So with in a very cheap format, you get a small tracer. And BPF has lots of helper functions. For example, there is this helper function BPF get current PID TGID. There are other functions like which give you directly the timestamp, and you can really like make a small tracer right there. So why do we need eBPF in tracing? So it's fast, it's very fast, and as I see things are being evolving, we would probably one day have like a script, you know, which is like a global tracing script which everybody uses. I don't know, it's a long dream, but probably it can come true. So we can add sophisticated features to tracing because BPF is really fast, so we can spend some time with the programs. Okay, we can have some stateful analysis being done. So for example, we can record system-wide sched breakups, but only when the target process is blocked. So instead of having like complete skate breakups being recorded, we can just record very small skate breakups. So we can utilize these side effects, or that's what I call, I don't have a formal name, or probably these actions, because it's a bit more, that's why I call it side effects. So we can use this side effects for assisted tracing. I'm going to talk about it a little bit later. So user space eBPF. So I recently did some experiments. So I created an experimental lib eBPF. It's like a user space eBPF. It's a direct port of the kernel eBPF, which was already there at the time. It's I think the 3.17. So it's really not new, but I used it just for testing the performance. So you can do like really good stuff with it, and you can essentially have the whole BPF but in the user space and just directly use it. So I used it for some performance analysis. So apply eBPF, LTTng, eBPF and eBPF plus jittered filters over it and measure the execution time plus the trace point time. So here's the small experiment which I did. So we have all these predicates P0 to Pn, and we can control how many predicates we can give. And we have the trace point time. So I calculate the TE plus TT and observe it for different conditions. So here are some results for it. So there was a 3x steady gain of 3x whenever we used the jittered eBPF. As you can see, with increasing number of predicates, the eBPF is really performing quite well. Whereas this is the eBPF interpreted. This is the black one is the eBPF jittered, and this is actually a hard-coded filter in C. So this was very close to a hard-coded filter. So we can see that, like, with very cheap we can, and dynamically with in a very inexpensive way, and still being dynamically, we can do filtering. So this is the comparison which I did with setting the LTTng's interpreter as well as the eBPF interpreter. So you can probably just look at this. This is the top bar is the LTTng's interpreter. Each time it was true for all the predicates, like from 2 to 9 predicates I checked. And then this is the eBPF interpreted. They are very close to each other. And then this is the baseline, that is LTTng without any filter. That's what I considered as the baseline. And these are for false filters. That means, and the false filters means that they are going to give you the true cost of interpreter run, because the filters are going to be false, so there is no trace point cost. So I found out that it was approximately 3.1x faster than the LTTng's interpreted bytecode. But there is some interesting thing. So JIT is really fast. These are my inferences which I drew from the experiments. So JIT is really, really fast. Okay. So I would like go on to say that it's the next thing after throw some cores or add some cache if you want some performance. So with small specialized interpreters which are like LTTng can be quite fast. For what is the need of LTTng right now for filtering? I think the interpreter which they have is really performing quite well, and probably they need not have a complete infrastructure like eBPF. But in the future cases, if they want to extend with more like a tracing language which is gonna generate the BPF bytecode and run like big executions, they could probably use it not just for filtering but for some other purposes. So let's see, I mean, we can probably, I'll try to integrate it with some real life benchmarks and see how it performs. So then in the end, I would say I did some very silly user space kernel eBPF and user space eBPF experiments, extensions. I don't know how much they are beneficial, but I still did that. So I took the syscall latency tracking use case, which Francois and Matthew already discussed. It's like just tracking the syscall latency, but what's with the latency threshold is like either defined statically or can be set manually. Okay, so but in real life we would probably, for different machines, we would probably have different normal levels of these thresholds. So I just thought that probably I can just use eBPF to set the thresholds, and this is very easy, but just by using maps and accessing maps in the kernel and just by checking, it's very easy. So but what I did is I used these side effects or the extra points in eBPF, and extended eBPF a little bit by adding my own small helper functions, which are gonna set thresholds. So for example, you have a user space eBPF filter which sets the threshold, and this threshold can directly be set in the kernel eBPF filter. A better elegant way is to not go through like a syscall, but have a shared memory in between the kernel eBPF and the user space eBPF, and both the filters can, through the helpers, can directly access. Yeah, it's not like a great design, but I just used it for checking, and I found out that the eBPF's syscall for just getting data from the maps was like 218 nanoseconds per fetch, whereas if you just use a direct shared memory, we all know that it's like 2-3 nanoseconds or something like that. So we can probably cut out some time, but I don't know if there is a really need for that. So that's all I have, and these are the references. I wrote some 2 blog posts about, you can get the experimental eBPF library, which is here. It's very unstable, I'm already telling you before. So, but I can make it stable if people want. Some people showed some interest in really having eBPF in user space, but I should tell that it's GPL code and you have to think about it. So I wrote 2 blog posts about BPF, and I'm going to write a series about it. So these are the first 2 parts, so you can go and check them out. They're about the internals of BPF, how they function, how its syscalls function and everything. So thank you, Efficios, Ericsson Montreal, and Diamond Work Group for having me here. Thank you. So any questions?
Yes. A question about eBPF. One restriction in the original BPF is that the program must always terminate. And you said that in eBPF, the restriction on backward jumps is lifted. So is it possible to have infinite loops in eBPF?
No, there is a check which is done in the BPF verifier which checks for that.
That's the very detailed verifier.
Yeah. I'm going to write the next blog post about the verifier, how the verifier works.
Excellent.
Yep. So, maybe this is a silly question, but I guess you're compiling this once when you first start up the application, so the overhead of that is insignificant.
Yeah.
Totally insignificant. Okay. It's interesting that there isn't already like a user space BPF library out there.
Experimental.
That's
yeah,
cool.
I mean, it works, but there are no defined APIs or anything, and it's code from 3.17, so I don't know if things have changed. Probably I can like update it if you want.
Sure.
Yeah, just one word about, well, the fact that this is GPL, that can be an issue for adoption at the user level, because then any proprietary application cannot link on that. So this is something we're very careful about in LTTng UST. The code is LGPL for that very reason.
I'd also say that, unfortunately, the Apache 2.0 license does conflict with GPL v2, although not with v3. So that's one other issue to be aware of.
Other questions? If not, thank you very much.
Thank you.